All right, let's dive in. If you want to unlock one of the most powerful ideas in modern cryptography, this idea of analyzing data while it stays completely private, you first have to understand the core components. So in this explainer, we're going to walk through the absolute fundamentals that make homomorphic encryption tick. Think of it like this. We have to learn the physics before we can build the engine.
So this all starts with a central question, really a paradox, that drives this whole field. How in the world can you perform computations, find insights, and analyze data that you are, for all practical purposes, completely blind to? It sounds impossible, right? But that is the exact problem we are setting out to solve. Okay, to even begin to unravel that paradox, we need to get one thing crystal clear: the two basic states that our data can be in. It might sound simple, but trust me, this distinction is absolutely critical. It underpins, well, pretty much all of modern cryptography. So on one side, you've got plaintext. This is just data as you know it. It's readable, it's an email, a number in a database, a medical record. Then, on the other side, you've got ciphertext. This is what plaintext becomes after you run it through encryption. It's been scrambled into what looks like total gibberish, and that's the whole point. It protects the real information from anybody who shouldn't see it. So the big question is, how do we reliably make that jump from readable plain text to secure ciphertext? Well, that brings us to our next essential building block. It's a really elegant mechanism that makes all of this secure communication possible, and it's known as public key cryptography. Now, the really beautiful thing here is the asymmetry of it all. The best analogy is a mailbox with a slot. Anyone in the world can walk up and drop a letter in that slot. That's kind of like encrypting data with the public key. But, and this is the key, only one person has the actual key to open the mailbox and read those letters. That's the private key. It's a brilliant system that lets anyone send you secure information while guaranteeing that you're the only one who can ever read it. Okay, so now our data is securely locked away as ciphertext. Awesome, but this creates a totally new challenge. Your standard math, addition, multiplication, it just won't work on this scrambled up data. We need a whole different set of rules, a special kind of arithmetic that can actually function inside this encrypted world. And this is the mathematical engine that drives the whole thing. Homomorphic encryption is built from the ground up on a concept called modular arithmetic. Now, don't worry, we're not about to get lost in a sea of equations. The goal here is just to build an intuition for it. And honestly, the best way to get a gut feeling for this concept is with an analogy you probably use every single day: a simple clock. It turns out to be a fantastic way to understand how numbers behave in these cryptographic systems. And this illustrates the core idea perfectly. I mean, think about it. If it's 9 o'clock and you add 4 hours, you don't get 13 o'clock, right? The time just wraps around to 1 o'clock. Well, modular arithmetic is exactly the same idea. Numbers operate within a fixed range, and when they go past the limit, they just wrap right back around to the beginning. This wraparound property is absolutely essential for computing on ciphertext. So we have our secure data, and we have our special clock math to work with it. We should be good to go, right? Well, not quite. There's one final, crucial piece of this puzzle we have to talk about. You see, in security, nothing is ever free. There's always an inherent trade-off that we have to understand and manage. And that trade-off has a name. We call it noise. The best way to think about it is as a small amount of random fuzz or static that gets intentionally mixed into the data during encryption. Now, this noise is what makes the ciphertext secure. It hides patterns. But it's also the main complication we have to deal with. It's both a protector and a problem, all at the same time. And here is the absolute crux of the issue. Every single time we perform a computation on our encrypted data, every addition, every multiplication, that protective layer of noise gets a little bit bigger. It compounds. And if that noise grows too large, it can actually overwhelm the original data, making it totally impossible to decrypt the correct result. So managing this noise growth is the central challenge in any practical homomorphic system. So there you have it. We get the two faces of data, plaintext and ciphertext. We have the public key puzzle for locking it up. We have the secret clock of modular arithmetic for working on it, and we have the critical trade-off of noise. With these foundational building blocks firmly in place, the question now is, are we ready to see how they all come together in the blueprint for homomorphic encryption?